Okay, so here's what we were talking about last time. We were talking about how to interpret divergence, right? So we have Gauss's divergence theorem written down. Remember, Gauss's divergence theorem is a relationship between flux and which is computed over a boundary surface, right? So we think of it as happening on the boundary surface, but then we realize, hey, it's actually an accumulating quantity. Boundary flux that you associate to a solid, that you actually computed on the surface, actually accumulates in the interior over that solid, right? And so you can think of that as adding up, kind of like mass adds up over little pieces, right? You think of it as a kind of a stuff, and you write a corresponding theorem, and there is a corresponding density, that being the divergence, right? And so flux then, well, I shouldn't circle these together, but there's a connection between flux and divergence. Flux is just the accumulation of little fluxes that are represented by their corresponding flux densities of divergence. Okay. All right, so that's just a quick reminder. So we made the observation that if you have a vector field representing the flow of a fluid, right, then flux just says how much fluid is leaving the region. I mean, this is a direct interpretation of what flux of a fluid field is how much stuff is per unit time, volume per unit time of stuff, let's say mass per unit time for this application, is leaving. So stuff per unit time leaving the region, K in here just for so I can ignore units, right? Okay. So, all right, take this and divide by volume on both sides, and this equation becomes that. Namely, it gives you a nice interpretation of divergence. You can think of divergence as telling you how fast is the density changing, specifically how fast is mass density decreasing. Okay, so, nice facts. We talked about that last time. There is an assumption that goes into this application, this analysis, this metaphor for divergence. And the assumption is that we have a fluid that can compress, right? Density can change. Density is not a constant. So this is reasonable if you're talking about the fluid of like air, right? Air can decompress or compress. If the fluid is, again, just sort of a tool for representing something like, a migration pattern of, birds in the air or whatever, right? You can have more bird density or less bird density. That's all perfectly reasonable. Okay. But what if you have a fluid that cannot be compressed, like water? What does divergence mean if you're talking about the flow of something like water? What could it possibly mean? Well, it certainly can't mean how fast is density changing. Density can't change. Right? Okay. There's another assumption that goes into this, and that is that there's no spontaneous generation of stuff here. Right? If you're saying, look, to whatever extent we have a flux, well, that means that there's less stuff remaining. There is no spontaneous generation of stuff. Okay, so what if we throw away both of those assumptions? And so we're going to talk about incompressible fluids. I like to think of this, another way to say, so this is incompressible fluids, so density doesn't change, right? But furthermore, steady state. Okay, so in other words, we're talking about some situation where there's a flow, right? But it's not like something's constantly changing, and we're talking about a steady state where, there's a flow, but that flow is constant at any given point in space. And furthermore, this is just a continuing process, and it's not like this is a momentary, shot of time, but this is a continuing process over time. Okay, so we ask the question then. What could flux possibly mean? I mean, let's draw this same picture here. We have a region, and if there's a flux outward, how could that be? How could you have an incompressible fluid like water, just steady state, continually just gushing out of this sphere? right? It doesn't seem physically plausible, right? So the idea is that, and maybe water's maybe not the best example for the following interpretation, but the idea is that if you have a positive amount of flux, such as what we have here, positive flux, that water's got to be coming from somewhere, right? So maybe there's a chemical reaction happening in here that's creating water, and the water is thus gushing out, something like that. Maybe it's just coming from the fourth dimension, something like that, right? Whatever, but somehow or another, there's a steady amount of water coming out. That means there's a steady amount of water being just originating in here so that we can achieve this steady state. Okay, so very often people will talk about a positive flux as being a fluid source. So anyway, it's common terminology. Heads up. Vice versa. What if the flux was negative? And let's draw that picture. If the flux were negative, and again, this is one of these sort of implausible, physically implausible scenarios. But what if this is your fluid? You've got a steady state situation. Fluid's just rushing into this region of space defined by this sphere, and never to be seen again, right? Right? It goes in, it doesn't come out, and it's not filling up. It's just water's just rushing in, steady state, nothing's changing. Well, then it's got to be disappearing spontaneously, right? And so we use the term sink, and this is a sort of a kitchen sink reference, right? So, water. If you look in your kitchen sink, water sitting on the surface of your kitchen sink, it all kind of flows toward the center. Right? And as long as you have the water on, the water's, maybe it's curving around in some way, but all the water is flowing toward the center, steady state. And then it just disappears in the middle. Okay. All right. So, that being the case, in the same way that, flux represents the amount of source or sink, right? Likewise, divergence being the associated density. You can refer, sometimes this pen doesn't work well, you can think of the divergence as being source density or sink density. Okay. All right, yeah?
Why is it with incompressible fluids we could just assume they can appear?
Oh, no, I'm not saying we can just automatically assume that. I'm just saying if you want to make this picture make sense, you have to assume that. Right? If you have a steady state situation of water all rushing in toward a region of space, just steady state, that's just okay, and this fluid's just going in there, but the densities aren't changing, well then it's disappearing, right? Because otherwise, with stuff flowing in, it's got to accumulate in there. The density would have to be getting higher and higher, but it isn't, right? So this picture makes no sense if you have an incompressible fluid, unless you assume that it's somehow spontaneously generating or somehow spontaneously disappearing. So I'm not saying that it does. I'm saying that if you don't assume that it can, then you can't draw this picture. Yeah. Okay. So remember, we're just talking about different ways that you can think about how divergence might sort of relate to a real physical scenario. By the way, let me give you an example of a fluid, and this isn't a constant density fluid, but anyway, a fluid that really does have a source. And we've talked about fluids don't have to be, these sort of, particle-less, smooth fluids. Like we think of water as being the smooth sort of, it's not made up of a bunch of particles, it's just this smooth thing. Of course, it actually is made up of a bunch of little particles, right? But nevertheless, we don't think of it that way. But we can also talk about actual, big things like birds or, fruit flies or whatever as being a kind of a fluid and sort of flowing around, right? Okay. Well, here's another situation, a couple of more situations where you can have such a thing. And the first one, a light bulb. I can't draw the new ones with the curly cues, so I'll draw an old style bulb. That light bulb, what does it do? It shoots out photons, constantly just emerging from that light bulb. Right? Steady state. It's not like the light bulb runs out of photons. Right? You just leave the light on, walk out of the room, come back, it's still shooting out photons. right? So this is a fluid source. A light bulb is a fluid source in that sense. Does that make sense? Here's another example, and I don't know how to draw such a thing, but if you have a radioactive material, right? Radioactive material just shoots out radioactive particles. Depending on what kind of material, different kinds of particles, right? But nevertheless, it just sits there and just, here comes these particles, right? Right. Okay. So another, you might say, fluid source. Okay. Okay. So let's talk about gravity. All the vector fields that we've been talking about so far have been fluids, right? Fluid flows. So we're going to talk about one now that represents forces. So this is a mindset shift, right? So go into this with the point of view of, okay, now this is a different thing. This is no longer talking about the flow of a fluid. Here we're going to talk about a force field. Okay. So here's a weird thing. Oh, by the way, so here's the formula then for the gravitational field. Couple little details I have to address. Y'all have seen this formula in, ninth grade physical science class, that the force of gravity is negative G M1 M2 over R squared. And that doesn't look exactly like this vector field that I've drawn here. So I want to address two issues. First of all, this here attempts to write down the gravitational field created by a single mass, right? This up here is a different thing. This is, how does that gravitational field created by this mass, M1, how much force does that apply then to M2, right? So I want to talk only about the field that's created by the one mass and not how the second mass, sort of experiences that. All right, so, for example, the Earth creates a gravitational field independent of whether I'm around. Well, that's true, but it also applies a certain amount of force to me, right? So these are addressing those two different situations. All right, so that's where the first, that's, why only the one M down here, and why I want this erased. There we go. Okay, the next thing I want to address is what's the deal with the cube down here versus the square there. That looks wrong. It looks like a sort of a transcription error. It's actually not. This is perfectly sensible. I'm going to rewrite this as negative G M over magnitude squared times x over the magnitude of x. And so what we have here, you'll notice, is a unit vector, right? X divided by the magnitude of x. That's just a unit vector. That's just indicating a direction. Magnitude is 1, right? And then the actual magnitude is inverse square, just as it's supposed to be. Okay, so it's sort of cosmetic, it's a little bit of an illusion there. This is not an inverse cube gravitational field. It's an inverse square gravitational field. Is everybody on board? All right. Okay, so anyway, this is the formula for the gravitational field. For a point mass M, located at the origin, and so thereby magnitude of x is the distance, because magnitude is distance to the origin. Okay. All right. Right. Okay, so weird fact. You take this vector field, its divergence is 0. Everywhere except for at the origin. Of course, now at the origin, the vector field's not even defined. And by the way, this is not something to be worried about. Yes, this vector field's not defined at the origin, but if you think about it, this vector field assumes we have a point mass, which doesn't really exist in the physical world. Right? There's no such thing as a single point mass. Mass comes distributed over space. Right? So, yeah, our gravitational field is, at the very, at the origin itself, physically implausible, and so therefore let's not worry about whether divergence makes any sense. The field doesn't make any sense either, right? So that ends up not being a problem. Okay, so other than that little annoyance, the gravitational field has divergence 0, which is weird. Certainly unexpected. This is a calculation that y'all can just do on your own. You can take this vector field right there, right? Keep in mind this x vector, this thing here is, x, y, z. Write out all the coordinates, compute the divergence, brute force, plug and chug. There's a lot of chug. It's a tedious little calculation, and you're going to fill up a page with algebra, and the result is all the terms cancel and you get 0. It's really quite surprising. Okay, so it turns out that there are some pretty interesting consequences of this. So this fact here, that the divergence is 0 away from where the mass is, allows you to draw some very powerful conclusions about how gravitational fields work. And we don't have time to go through all these details. Wish we could. This is a fun little exercise in physics, but we just don't have time in the schedule. And by the way, let me strategize for you a little bit how these arguments work. Vector fields relate to divergence by way of a formula. Right? Vector fields relate to flux by way of a different formula. Divergence relates to flux by way of Gauss's divergence theorem. So what we have is 3 connected things: the field, the flux that you might be interested in of that field, and then the divergence of that field. They're all kind of in different ways connected to each other. So the way that you get some amazing results out of the fact that the divergence is 0 is taking advantage of these various connections between these 3 different things. You can use what you know about divergence to help you understand flux. You can use what you understand about flux to help you understand divergence sometimes. And what you understand about divergence can help you understand the field. And by way of understanding flux, playing games about how these things connect to each other is how you get these arguments done. So anyway, again, we don't have time for that at the moment, but some neat facts, and I'm just going to write down what the results are. If you have some region like this, and if there's some mass around, maybe there's no mass, maybe there is some mass, but just as long as there's no mass no mass inside of this solid region. Right, so I'm going to draw some mass now. Let's say the mass is over here. Right. Well, the mass creates a gravitational field. There's this really strong gravitational field when you're close to the mass. And then it's a weaker gravitational field when you're farther away. Still points toward the mass. And then it's a much weaker gravitational field, this itty-bitty, teeny-tiny gravitational field when you get further away. Right? It's a complicated field. This is a complicated surface, this weird little sort of kidney bean-shaped thing. Right? You imagine having to parameterize that surface. There's going to be all kinds of who knows what sorts of weird in the parameterization of that surface. And then the vector field has a cube and a square root in it. Yikes. Right? So the vector field's ugly, the surface is ugly. Can you imagine trying to compute that flux? Well, with clever arguments, you can easily conclude that in fact the flux through this surface is 0. Right? It would be a tremendously difficult calculation to do brute force. I'm going to show you this one because it's just really quick and easy, and this is just easy to do. So the idea of this argument is, let's just address this solid. Right? Let's write down Gauss's divergence theorem as it pertains to that solid. Let's see. I guess where do I have? I'll just squeeze it in over here. The divergence theorem as it applies to that solid. Oh, I shouldn't use green. we'll use orange, is flux through the boundary of R. Here, I'll say boundary of R. Flux through the boundary of R is triple integral of divergence which is 0. We're taking a triple integral of 0. Flux is 0. We're done. Right? How's that for a quick bypass of what otherwise would be a brutally inconvenient argument? Okay, so really neato. A related scenario, suppose that there is some mass on the inside in addition to some mass on the outside. And I think this is also pretty plausible. All the mass that's on the outside, let's see here, my picture's getting a little messy here. Let me clean up my picture. This mass that's on the outside doesn't affect the flux. Now, the mass on the inside is going to create some flux, right? I mean, that's absolutely the mass on the inside is going to create some flux. And you can't do a divergence argument with mass on the inside because, well, the divergence isn't defined at that point. Therefore, you can't do the triple integral. You can't say triple integral over solid if your integrand is undefined near a given point. So Gauss's divergence theorem crashes and burns there. But a more detailed argument that we have time to go through here reveals that whatever mass is on the outside, you can just ignore it. Only the mass inside matters. And furthermore, only the total amount of mass on the inside matters. So if I were to take this mass and move it down over to here, whatever, the flux through the boundary surface that is unaffected. Okay. Again, wish I had time to go through those arguments. Okay, so another true fact that and if you keep tugging on these threads and you keep making arguments, drawing these kinds of pictures, another neat fact you can get to is you can not only can you tell that only the amount of mass inside the surface affects the flux, you can actually write down an explicit formula for how exactly does the total amount of mass affect the flux. And the explicit formula is flux is negative 4 pi g times the mass. That's it. This mass being the mass on the inside. Right, just the mass on the inside, not the mass on the outside. Cool fact. Yeah, everybody happy with that? By the way, why that's true, not at all obvious. That's there's work that goes into that. Yeah.
So, should we be able to understand why the mass outside R doesn't affect it?
It's just this picture that I drew. So when we were talking about, here's this scenario, right? And this mass creates a gravitational field, and I claim that, if you look at the gravitational field created by that mass, the flux is 0. And so the idea is simply that, well, if there's all of a sudden some new mass inside, well, how much gravitational field is created by the old mass? Unaffected. Right, so this mass here, yeah, it's going to create a gravitational field. Yeah, there will be some field lines crossing the surface there. There will also be some field lines crossing the surface over here. But Gauss's divergence theorem, as applied to this solid, says flux is a triple integral of divergence. Divergence is equal to 0. Therefore, flux is 0. Yeah. So the what's contributed to flux from that mass, Gauss's divergence theorem says it makes 0 difference.
Even if you have the vector field going through the region?
Going through what?
The vector field kind of affects the region.
Oh, it does. Well, so now so you remember we were talking about how, so you've got the field, and then you've got the divergence, and then you've got the flux. And all three of these things are different quantities, but they're all related to each other. So I'm not saying the field is 0. You're quite right. There's a non-trivial field there. There's a non-trivial field there. This green gravitational vector field is non-zero everywhere, right? Not saying the field is zero. I'm saying the flux of the field is zero. The reason why is because flux is an integral of divergence. Divergence is zero, therefore flux is zero. So another way to say that is to whatever extent there's flow into the solid region there is a corresponding flow out of the solid region there. Yeah, and how does this balance off? You got some positives, you got some negatives, and I'm making the assertion that Gauss's theorem backs us up on that, well, they have to all cancel because there's no divergence inside. Therefore, the total flux has to be zero. Yeah.
So does this mean like gravity acts like almost like particles?
It does, and I was going to get to that. So no, that's a fantastic insight. So thank you for making that observation. That segues very nicely. So yeah, it's just like as if. And now let me. Well, before I get to that, let me confess it is a little awkward that gravity points toward the mass, not away from the mass. I mean, it's very convenient for our purposes living on planet Earth, right? But it is awkward here because we think of let's imagine there's a light bulb right here. If there's a light bulb right there, well, the light bulb creates a flow, and y'all are aware. I think you're bound to be aware that when you're close to a light bulb, it looks brighter, right? And when you're really far away from the light bulb, it looks dimmer, right? So the field is actually stronger near the light bulb, and then it gets smaller as you go away, right? But it remains that a fluid is emerging from this light bulb. Right? This fluid of photons. Well, all of these results apply in exactly the same way. So the analogy is very strong. The way mass and its resulting gravitational field behaves is just like the way light bulbs and their corresponding light fluid fields, photon flow fields, whatever you want to call them, behaves. So let's think this through. If there's no light bulb inside of that region, what's the flux? What's a total flux through this region? Well, look, there's going to be some inward flux there, but there's corresponding outward flux there. I mean, look, think about it just from the point of view of one photon at a time, right? Of any one photon, it's going to flow into the surface, and then it's going to flow out of the surface. Just as much photons are going in as are going out. We're not accumulating photons inside of here, right? So the flow out, the flow in are exactly equal. Flux is zero. Just like with gravity. Right? So yeah, and then likewise, if you had oh man, I deleted my thing. If you had a come on, eraser. If you have your light bulb on the inside, what's the total flux of photons through the surface? Well, how many watts are on your light bulb? Right? However many watts are on your light bulb, however many photons are shooting out of your light bulb, that's going to tell you the flow of photons out of your surface. Right? What would happen if I took that light bulb and put it down here? It's still shooting out the same number of photons. We're still going to have the same photon flux out of the surface as we otherwise would have. So only the total amount, not the distribution, affects the flux. Okay. So it's a great observation. Gravitational fields behave like the flow of a fluid like photons, or a radioactive flow of radioactive particles, something like that. So in fact, they have a name for this, for these imaginary. I mean, this fluid, whatever this fluid is that the gravitational field is supposed to be representing, the particles that make up that fluid. So the theory goes, they gave them a name. They call them gravitons. Right? So the idea then, and we're well outside of my area of awareness in physics, but to my knowledge, I don't know if there's any actual evidence that these things exist. But man, gravity sure does work as if there were gravitons being shot out of mass in the same way that photons are being shot out of light bulbs. And so the theory goes, again, you have a mass here and you have a mass here. How does the force get communicated between these two? How does this mass know that there's a mass over here that's pulling on it? This is the whole action at a distance problem, right? So one of the theories is, well, the way it knows is because this mass fires out a graviton that hits it and tells it, hey, by the way, come this way. Right? And anyway, the flow, the divergence, all these rules about flux, very consistent with that. Okay. So here we are again with a statement about flux. As we've done before, sort of divide by volume on both sides. Imagine the balls shrinking, etc. And you get this corresponding suggestion about how to interpret divergence. Divergence is proportional to mass density. Okay. Which, by the way, fits in pretty nicely if flux is proportional to mass. By the way, again, perfectly plausible. If you think of mass shoots out this fluid, thus creating the flux, more mass, more flux, right? Highly plausible. Then likewise, flux density is proportional to mass density. Well, of course it is. The mass is creating the flux, and so the density of mass creates the density of flux. Okay. All right. Okay. Let's see here. I have spent too much time on that little discussion of gravity, so this next page here, I'm just going to skip this. If you're curious, this is a cute little argument. It's not in the book, but this is something I think is it's kind of neat. You ask this question, and I'll spend a few seconds on it, but I'll be very quick. Can you find an anti-divergence? And how do you know you can find an anti-divergence? What's the plausibility argument that could be made to suggest that you should be able to find an anti-divergence? Right? A vector field whose divergence is whatever function you're interested in. So the answer is yes, and the clever move is to sort of take advantage of this fact here. Notice what this is saying is that density creates divergence. If density creates divergence, then what that means is the gravitational field created by your density has divergence, which is that density. Said differently, a density distribution of mass creates its own anti-divergence physically, which is pretty wild. I think that's kind of neato. Anyway, all the details are here, and it's just details, so let's not sweat it. And this is not in the book, and you're not responsible for knowing this, but I think it's kind of cool. I'm a big believer in the following last observation I'll make about this, and that is, if you want to have sort of a physical metaphor, how do you think about divergence? Mass is a great way. It's a great physical metaphor because of this fact right here. This fact right here. What does divergence look like? Divergence looks like density. Some constants involved. Whatever, those are constants. Divergence looks just like mass density. Mass creates a gravitational field. That gravitational field has a divergence. The divergence is the density. So here's another way to say it. Divergence relates to a vector field kind of in the same way that mass density relates to a gravitational field. If you want a physical metaphor for divergence as relates to a vector field, The physical metaphor is think about how mass density relates to its resulting gravitational field. Anyway. Okay. All right, let's talk about electric fields. This is probably more relevant, I suppose, unless you go into being an astronaut, right? Gravitational fields are pretty boring, right? I plan to not ever leave the surface of the Earth significantly, right? Therefore, gravitational fields will always be constant in my personal experience, and constant vector fields are really easy to understand. So, okay, but electric fields, not so, right? A lot of the stuff that y'all engineers manufacture and make, it's very important to know how electric fields work. Because electric fields are what makes your stuff work. I mean, a lot, right? Okay, so here's the formula for an electric field created by a charged particle. And what you'll notice is that this is morally identical to a gravitational field. It's got that same structure. Okay, sure, a different constant out front, but that's just a constant, right? It's just a scalar factor. Structurally, an electric field is just exactly the same as a gravitational field. And so I think this is a big lesson. I got a lot of good out of this when I was, again, doing physics a long time ago. And that is, trying to visualize what electric fields look like. I would just think, all right, well, they look just like gravitational fields. But, a minor difference. There's no minus sign, right? Electric fields you think of as pointing outward instead of inward. Okay, yeah, sure, right, a little different. But the hard part about understanding electric fields, just like gravitational fields. So here's the thing. Having made that observation that they're structurally identical, all of this stuff that we were talking about with gravitational fields, where you're thinking, I'm not going to do any interplanetary exploration. I don't need to understand that, right? Well, that was a metaphor for this stuff that you do need to understand with electric fields. Divergence is 0. Same exact calculation, just, multiplied by a different constant. All these results, if there's a surface that doesn't have any charge inside of it, the flux is 0. Gauss's divergence theorem. Whatever charge is on the outside doesn't contribute to the flux over a boundary surface. Only the total amount of charge inside matters. Doesn't matter where inside. Again, think about light bulb metaphors, right? It's the same thing. I mean, it's physically we don't actually visualize charged particles as shooting out a flow of a fluid, but they behave as if they are, right? Just like with gravity, just like with light bulbs. And in the same way that gravitational flux is proportional to the mass, well, again, sure it is. Mass is what's creating this flow. The flux of that flow then is proportional to how much mass is creating it. Flux proportional to mass, very plausible. Ditto for electric fields, except now it's charge. Q represents charge. It's charge that's creating this electric field, and therefore the total flux of the electric field is proportional to the charge. Different constant. Yeah, right. Details. Right. But structurally the same. And likewise, if flux, let's see here. So if this says flux is proportional to charge, right? Then along the same lines, flux density, divergence, proportional to charge density. So we use this little letter rho, standard choice anyway. A little unfortunate, right, with spherical coordinates and all that, but anyway, it's pretty standard. Rho represents charge density. And so same sort of plausibility argument as to why divergence should be proportional to charge density. Well, because flux is proportional to charge. So, yeah. Okay. All right. Now, since we can, while we're here, I do want to show you this calculation. This is wonderfully convenient calculation. Very interesting. It's amazing that this powerful calculation can be done so conveniently. So as I often do, the first thing I'm going to do is try to persuade you of how hard this calculation is going to be, right? And then I'm going to do it in like 2 lines, right, with clever arguments. So here's the problem. Suppose you have a sphere that has charge uniformly distributed over the surface of the sphere. So it's like you have a metal sphere maybe, right? And it's got charged particles in it, and they're uniformly distributed, which of course they would be. Charged particles tend to repel each other, so they distribute uniformly. Okay, so uniform distribution of charge. Well, here's the thing: this that little electron right there. See that one electron? That's creating an electric field. Oh, wrong way. Sorry. That's creating an electric field. Okay, let me do this with the pencil. It's creating an electric field. That little electron right there is creating an electric field. That little electron right there is creating an electric field. You see the problem, right? There's infinitely many little infinitely small charged particles, each of which is creating its own little electric field, and they're in different places. So it's not like they all sort of are exactly the same and on top of each other. They're pointing in different directions. So for example, at this point right there, well, this particle is making the electric field that way, but this particle is making an electric field that way. Right, so they add in these weird ways based on the fact that these charged particles are all located in different places. So we have this inverse square electric field created by each little charged particle, of which there are infinitely many distributed in a weird way in space. What's the total, right? What's the actual, like if I'm sitting at, let's say, right here inside the sphere, what's the grand total of all of the electric fields created by all these different particles, right? So at that one point, missed it. Okay, let's try that again. Here, let me cheat. There's that coming from the first particle, and then there's that coming from the other one, and then there's that coming from the other one, and there's this other one about like that coming from that one. All of these different field lines coming from all these different particles, how do they add up? What is the actual electric field at that point? You see how this would be a really, really, really hard problem? I mean, if you brute force this, you've got imponderably difficult problem. Right? I think that's a fairly easy pitch that this is a hard problem. Okay. Now let's solve it in 2 lines. I can erase all of this. Here, let me do it like this. There we go. Okay. So, first, the grand total, right? Forget about the individual particles. Grand total, the electric field, I claim, has to be what I'm going to call radial. The electric field's got to point along this axis line, and it's just a symmetry argument. And by the way, I don't want to make a mathematical symmetry argument. I'm just going to make a physical appeal here, right? And the physical appeal is this is a uniformly charged sphere. If I were to sort of turn that sphere, rotate that sphere around, I'm not really doing anything. I mean, so how could the electric field be anything but directly away from the origin or directly toward the origin? We're still not sure which of those, but it's going to have to be on axis, just for the symmetry of the situation. So that's the first appeal. Okay. All right, next appeal is let's think about, now a reminder, here's where our charged particles are along the edge. There's our charged particles. And let's suppose that at, let's say, that point, for example, the vector field is like that. Well, then, again, symmetry would say that it's got to be kind of, I'm going to say, equivalently radial everywhere else on this little small sphere. Now I'm choosing to make this small sphere that contains this 1 point that I'm interested in, let's say right there. So you pick a purple point, draw the blue sphere that goes through it, centered at the origin. The field lines are going to have to look like this. They're radial and kind of all pointing outward. Or inward, we don't know yet, but one or the other. Yeah? Everybody on board? All right, so we're practically done at this point. Look at what we have a picture of here. On this blue sphere, there's a flux through that blue sphere. Right? I mean, look, we've got all these field lines pointing outward. That makes flux. How could there be flux through that blue sphere? There's no charge on the inside, right? That blue sphere, there's no charge on the inside of that blue sphere. All the charge is around the outside edge, right? So there's no charge inside, therefore no flux through that blue sphere. And if the flux through that blue sphere of our green vector field, if that flux is 0, that means that the field length has got to be 0. So the vector field is 0. It adds up to 0. Isn't that cool? I think that's awesome. By the way, here's another situation where I think it's fun to think about the relationship between electric fields and gravitational fields. So instead of thinking of this as a bunch of charged particles around the surface of a sphere, let's think of this as being a bunch of mass uniformly distributed in the shape of a sphere. Right? And so I like to think of like a little Star Wars reference, like the Death Star, right? So there's this spherical shape of mass, but it's hollow on the inside. That's kind of like this. So what this is saying is, with mass distributed, and let's say uniformly, and it's probably not, but anyway, mass distributed uniformly around in a spherical shell, like the Death Star, inside of there'd be no gravity. Grand total gravity would be 0. Said differently, wherever you might happen to be, let's suppose you're at this point inside of the Death Star. Well, these points over here are pulling you very strongly in that direction because you're really close to these little pieces of mass. And so there's a temptation to say, well, come on, surely there's got to be a strong gravitational field toward the near edge wherever you are, right? But there's so much more mass over, I need a color, I'll use blue. There's so much more mass over there. It's a lot more mass. That whole far side of the Death Star, that's a lot, right? And sure, it's farther away, but that's pulling you the opposite direction. And it turns out that grand total, when you add this up over all infinitely many pieces of mass, it adds up to 0, yeah.
How does the part about it being radial relate to this?
Yeah, so I have to use the radial to be able to draw this conclusion. I want to be able to say that, because the flux is 0, therefore these field lines have to have length 0. I have to eliminate the possibility that there's something like that going on. Right here, you could have a non-zero field that's still giving you 0 flux. Right, so the fact that all these field lines are radial is what makes that problem go away. Yep, it's a great question. Okay, all right, so we'll call that a day, and y'all have a great weekend. See you later.